Okay. So I will switch to our next topic. So yesterday I have mentioned that if I am given a couple of stacks, okay, then a Turing machine can be simulated, right? Today what I will start with, I will simulate a single stack by two counters, okay? And to that effect, let me introduce the concept of counter automata. They work as follows. Let me follow the slides. Let us take some fixed positive integer k. Okay. And a k counter automaton, okay, is an automaton that consists of these things. One, a one-way read-only tape where the input is supplied, usual thing. And if you choose, this head may be two-way, but it doesn't matter. We will stick to one-way thing. And k counters capable of storing non-negative integer values. Okay. So it's no longer a stack, but just a counter, integer counter. 0, 1, 2, 3, and these integers can be arbitrarily large. Okay. And these counters can be independently operated, and some 3-4 operations, each counter supports independent of other counters. Okay, so these are these operations. Check whether the counter value is 0 or non-zero. Okay. And find the least significant bit of the counter. Okay. So least significant means the rightmost bit. And increment, decrement. Plus, plus, minus, minus. Okay. So these are all the operations that each counter supports. A very, very primitive set of operations. Check for 0, find the most significant bit. Actually, the second thing is not necessary. You can actually figure out the least significant bits if you are given the first one, third one, and fourth one. Okay, but anyway, let's have it handy. Find the least significant bit. So that's the basic thing. So it's a machine with a finite control, a read-only input tape, which may be one way, okay, and k number of counters supporting these 4 primitive operations. Okay, that's all. A very, very simple machine. Okay. And let us see, if I take k equal to 2, then this counter automaton becomes something like as powerful as a Turing machine in terms of language recognition, but they will be very, very slow. Anyway, slowness is for the moment not a matter of concern to us. Okay. So, to start with, we have seen that the tape of the Turing machine can be simulated by 2 stacks, right? Now, if I can simulate some stack, either the left stack or the right stack, by some number of counters, then I can simulate the tape using those counters, right? So how to do it? So this involves some kind of formalism. Let us do it one by one. So let gamma be the stack alphabet. Okay. And depending upon the size of that gamma, I can use a fixed number of bits to encode the symbols of gamma. Okay. In particular, if the size of gamma is something like g, then log of g, ceiling of that, those many bits suffice for representing all the symbols. So in the range 0 to g minus 1, something like that. Okay. And let us say that that is called L. These many bits are sufficient for storing the symbols of gamma. Okay, straightforward. And therefore, instead of pushing and popping symbols to the stack, I can view this as a stack capable of storing just bits. Okay. So if I want to push a symbol of gamma, this is equivalent to pushing L bits. Okay. Likewise, if I want to see what is on the top of the stack, I have to extract L bits from the top of the stack. And in L is a constant, therefore this counter automaton can remember what bits are read in its finite control, and it can figure out which symbol it is currently looking at the top of the stack. Okay. So I just introduce this notation A within a pair of parentheses to denote the L bit representation of A. Okay. It may be 0, 0, 0, 0, L zeros, or maybe as big as 1, 1, 1, 1, all ones, L ones. Okay. So if the stack is supposed to store these symbols A1, A2, AK, this time I am just making a change of convention. I am printing the stack from bottom to top. So AK is the topmost symbol, A1 is the bottommost symbol. Okay. So instead of storing this symbol followed by this symbol followed by this symbol, it will store this KL bits, the L bits corresponding to A1, L bits corresponding to A2, and so on. Okay. And correspondingly, when this is the content of a stack, okay, my counter will store the same bit sequence, but I just insert 1 at the beginning. Otherwise, there may be some trouble. What is the trouble? For example, let's say the bottom marker has L bit encoding 0, 0, 0, 0, 0, 0. Okay. If I straight away convert that to an integer, it will be 0. But the empty stack is also 0. Right. But if I just add 1 at the beginning, then this may be 0. This may be something. So leading 0 bits, in order to handle that, I will just associate this bit string stored in the stack with this counter value. This is a positive integer. 1 followed by L bit pattern, followed by another L bit pattern, and so on. Okay. And K may even be 0. Okay, the empty stack is now 1. And the bottom marker, if it has 0, 0, 0, 0, L, then this stands for 1 followed by L zeros. So now I can distinguish between these two. Okay. And as I mentioned, obtaining the top is in popping and remembering L bits. And this remembering can be done in the finite control because L is, after all, a finite quantity. Okay. Pushing means if you want to push a new symbol, just push L bits. Okay. So this formalism, or I would say simplification, lets us assume that it's a bit stack. So it suffices that I can push or pop bits. I'll look at the most significant bit on the top of the stack. Not most significant, least significant bit on the top of the stack. Okay. But the convention is now I am listing the symbols or their bits from bottom to top, not from top to bottom. Okay. Okay. So what will happen in this simulation when this stack is supposed to contain this or equivalently this, okay, this symbol string or this bit string, one of these two counters that I am going to use will store exactly this value. and the other counter will store 0. Okay. And then let us see how we can implement push and pop. Okay. So pushing or popping a bit to the stack or from the stack. So let's assume that the counter C stores that value 1 followed by the scale bit. Okay. And the counter D is 0. Okay. And I want to push, like let's say a bit B, which is either 0 or 1. Okay. Then what will happen? Essentially, followed by this, there will be a new bit B. Correspondingly, this value will change to 1 followed by this, followed by that new bit B. Okay. So let us see how we can do it. Okay. So D is 0, C is starting from the value that the counter or the stack is supposed to store. Okay. Now, look at this kind of simple program, which the counter automaton can definitely do given the 4 primitives: check for 0, increment, decrement, and look at the most significant bit. Here I do not need to look at the most significant bit. So what I do, I decrement C once. For each decrement, I am incrementing D twice. Okay. So when C becomes 0, D stores the value 2 times C. Okay. And then if the new bit is 1, I just increment the value of D by 1. Otherwise, just keep it as it is. Okay. So this is how push can be simulated using 2 counters. One counter stores the original value, other counter is always 0, and then in this, using this loop, I eventually prepare D to the new value of the stack or the counter, and in the process C has become 0. Okay. And this is the pop operation. Okay, it's essentially the same thing. You decrement C twice, increment D once. That is essentially division by 2, right? Okay. So push and pop can be done. Okay. And then what happens after a push or pop operation? C becomes 0 and D now stores the new value. Okay. So what can I do to handle this? One possibility is that I move the value of D to C once again by a loop like this. While D not equal to 0, decrement D, increment C. Then the value of D will go to C. Okay. And C becomes 0 again. Okay. Can you visualize this? Yeah. Or another option is, instead of doing this, I will just change the roles of C and D. Okay. Just interchange the roles of, switch the roles of C and D. Okay. So push and pop can be implemented using a counter with certain association of the values stored in this stack with positive integers. Straightforward, right? So now let us come to the conclusion. The tape of a Turing machine. Okay. So one tape is essentially equivalent to 2 stacks. Okay. And one stack is essentially equivalent to 2 counters. Okay. So the Turing machine tape can be represented by 4 counters. 2 plus 2, 4. Okay. A stack is equivalent to 2 counters. Tape is equivalent to 2 stacks. So a total of 4 counters is sufficient to store the content of the Turing machine tape. Okay. But if you see each stack operation, push or pop or whatever, okay, they actually use one helping counter, okay, just to do that operation, okay. So C has two, I mean, the first counter has two C and D. The next one has two things, E and F, okay. And D or F, they can be combined together actually. I can use only single helping counter. Two counters are not needed, right? Okay. Therefore, actually, for each stack, only one counter stores the content. Other is always 0. Okay. Except during this push or pop operation. So I can actually, other counter helps in implementing the push and pop operations. Okay. And we can use a single helping counter for both these stacks. So that reduces the number of counters from 4 to 3. Okay. So only 3 counters suffice. And the final conclusion is that a 3 counter automaton is as powerful as a Turing machine in terms of language recognition. Okay. But the way a push and pop is done, you see it's very, very slow. Okay. So one by one, all these integer values will come from here to the other counter. Okay. Whereas in a real stack, push and pop can be assumed to be something like a constant time operation. Or if you are looking at stack storing bits, it's basically L bits are there. So each push and pop can be thought of as a big O of L or big theta of L time operation. Okay. So it's very, very slow. But once again, let me highlight that for the moment, I am not worried about speed or running time. It can do it in a very, very slow manner, but it can do it. It can simulate the type of a Turing machine using only 3 counters. Okay. So in terms of language recognition, they are equivalent. Okay. So now finally, how I can reduce the number of counters by just 1. So 3 counters suffices, we have seen. Now, with some trick, I can reduce the number of counters even by another 1. Okay. Okay, so let's say these counters store the value I, j, and k. Okay. 3 counters, I will manage with only 2 counters. And these 3 count values are I, j, and k. So I represent this I, j, and k by this integer 2 power I, 3 power j, 5 power k, and stored this value in a single counter. Because of unique factorization of positive integers, this representation is unique. 2 power something, 3 power something, 5 power something, those 3 somethings will be uniquely determined by the counter value. Right? Okay. So this is the storage, I would say, trick. And so we will use this single counter storing this value, which has in its, I would say, in it embedded these 3 exponents I, j, and k, which can be uniquely determined. Okay. And the other counter that I will use is to do this operations on these counters. Okay. So now only 2 counters. One is storing this value, and the other one is the helping one. Okay. So we use the second counter to do arithmetic on ijk. Not exactly arithmetic, whatever operations are supported by this each counter, those things. So here is an example. Let's say how we can implement the operations on j. Okay. So use the push pop kind of loops. While something is not equal to 0, then keep on doing something. So I am not giving you the exact codes. These are fairly straightforward. So check for 0. When I am talking about the second counter j, so it's
Hello, sir. Okay, load. Hello.
Hello?
Yes, sir, you are audible, sir.
Okay, so at last power is back. Okay, let us restart. Okay, so once again, is the recording still going on? Oh, it's still going on. I don't know what was happening. Anyway, let me once again. Huh? Okay, so let us continue. Okay, so where are we? Okay, so we are planning to uh, manage 3 counters using only 2, and that was the scheme. And I will now show how I can, for example, work on this counter J in this mode. Okay, so J means this is the power of 3. So what are the 4 operations? First, check whether J is equal to 0. That is just checking the divisibility of that quantity by 3. So divide by 3 using that counter loop. Okay. If you get 0 remainder, you know it is divisible by 3. Otherwise, it is not divisible by 3. So it's doable. Very, very slow, but doable. And find least significant bit of J, assuming that J is greater than 0. That is basically check for divisibility by 9. Yes or no? If J is an even number, this quantity is 3 square power something. Okay, so if it is divisible by 9, the least significant bit of J is 0. Otherwise, it is 1. Okay. And of course, the assumption is that J is greater than 0. Okay. Otherwise, you cannot extract this significant bit if nothing is there. What? No, that entire quantity. No, that entire quantity. 2 power I, 3 power J, 5 power K. If, no, look at this. 2 power I, 3 power J, 5 power K. So what was your question? The second one. Okay. So if J is odd, now this 2 power I and 5 power K, they do not contribute any factor of 3. So if J is odd, so it will be of the form 2 power something plus 1. So it will not be divisible by 9. On the other hand, if J is even, let's say 2R, then this is 3 power 2R, which is 3 power 2 whole power R. It's divisible by 9. Other things, they do not contribute any factor of 3. Right? Three power 3. So am I making any mistake? 3 power 3 is divisible by 9, right? How do I check it then? J is greater than equal to? No. How do I do it? Okay, so I see. So that's fine. Actually, How do I find the least significant bit? Okay, so one possibility may be keep on dividing by 3 and remember the parity of that exponent. Huh? That is also that's yeah, whatever. Yeah, you could keep on dividing by 9 and finally, yeah, something like that we have to do. Okay. So this is not a correct thing. Anyway, I will correct it. Keep on dividing by 9 and until it becomes a multiple of 3 just or 1. I mean 3 power 0. Anyway, fine. Okay, so j plus plus is just multiply by 3. J minus minus is divide by 3. And again, it is allowed only for j greater than 0. Okay. So therefore, by maintaining this single count, I can do it. Okay. And as you see that this 2 counter automaton is even slower than the 3 counter automaton. But anyway, in terms of language recognition, no problem. Okay. Okay, so a 2 counter machine, although extremely slow compared to a Turing machine, can still have the same language recognition capability as Turing machines. And I am not looking at the reverse direction, but because a Turing machine can definitely maintain these counts. It's fairly straightforward. Okay. Okay, so that leaves us with another particular kind of machine. So these are Turing machine-like machines, but they are not accept or reject machines. But instead of accepting or rejecting strings, they actually enumerate strings. Okay. Yeah. So it consists of the following. So these are the basic ingredients. A finite control, which operates very similarly like the finite control of other machines, like Turing machines. Now it has 2 tapes. Okay. The first tape or the top tape is called a work tape, and it is a read-write 2-way tape, like a Turing machine. Right. Okay. And there is another tape which is called the enumeration tape or output tape. So it may be 2-way, 1-way, whatever, but it is only a write-only tape. Okay. So this enumeration machine can only write symbols on the write-only tape, output tape. Okay. And the only symbols that it can write are the symbols of sigma. Okay, the input symbols. Okay, so the work tape is like a Turing machine tape. Other tape is actually meant for enumeration. So it can only write symbols from the input alphabet on this output tape. There are no accept or reject states because these enumeration machines do not accept or reject anything. Instead, there is a start state as usual and a specific state called the enumeration state, E. Okay. Now, what this machine does is from time to time it enters this enumeration state. Okay. Okay, so let's make it more formal. It starts normally in state S, okay, with both the tapes empty, okay, and then it follows the standard transition procedure, okay, where only the symbols written in the work tape are considered for its transition because the output tape is only write only. You cannot read anything from that. Okay. Then he proceeds as dictated by the transition function, and from time to time, the machine writes to the output tape. No, not work tape. It should be output tape. So this is a mistake. Some transitions let the machine write to the output tape. Work tape, of course, it's like a normal Turing machine tape. It can read, write, do anything there. But from time to time, it will write to the work, not a work tape, output tape. Okay. So there are two mistakes in this on the previous slide. Okay. And from time to time, it will enter the state E, the special enumeration state. And whenever it does so, whatever is written in the output tape, it is said to be enumerated. Okay. So the content of the output tape is enumerated. Okay. So that is the string that gets enumerated. Okay. And the output tape is erased and the head is positioned to the beginning. Okay. So this machine keeps on doing this thing. And once again, it jumps to some non-enumeration state and keeps on doing this thing. Okay. So once again, it writes something on the output tape. And once again, it may go to E and enumerate that other string. Okay. So we may keep on doing this enumeration forever. And the language of E is the set of all strings enumerated by this machine E. Okay. For example, you can think of an enumeration machine for A power n, B power n, C power n. So it maintains that n as, let's say, 1, 1, 1, 1, 1, 1 on the work tape. Okay. So you have n ones on the work tape. Okay. So you make a pass. You know how many ones are there. Write those many A's. Make a reverse pass. Okay. As many ones are there. Write those many B's. Okay. Then once again make another pass. So write as many C's. Okay. And then you go to the enumeration state. So one particular A power n, B power n, C power n is enumerated. Then you go to the work tape. Just append another one. Okay. So next time you will enumerate n plus 1, bn plus 1, cn plus 1, and keep on doing this forever. Okay. So that's an example. And I will now show that for every enumeration machine, I can build a Turing machine, okay, having exactly the same language. Turing machine's language is defined by acceptance, okay, whereas enumeration machines, acceptance is defined by enumeration, okay. So I will do two-way things. Given an enumeration machine, I will build a Turing machine having exactly the same language. And given a Turing machine, I will build an enumeration machine having exactly or enumerating exactly the same strings. Okay, so the first part is slightly easier because I can think of okay, let's see. Formally, let's see. Okay. So I may construct this AIM as a 3-tape machine. Now this is a Turing machine. So it will accept if and only if, accept its input if and only if that input is ever enumerated by E. Okay. So it is given some input, let's call it X. Okay. So it stores this X somewhere, maybe on the 3rd tape. Okay. So M copies X to its 3rd step. Okay. And then it erases its 1st step. The input is provided to the 1st step, so it erases it. Okay. And anyway, the 2nd tape is empty to start with. Okay. So M will now use its 1st step as the work tape of E. It can do it. It's a normal read-write tape. Okay. And it will use its 2nd tape as the output tape of E. For a Turing machine, this is read-write, but it can anyway use that tape in a write-only mode. That's not a big issue, right? Okay. And then it will keep on simulating E, okay, by following its transitions, which may be in the head of M. The finite control can embed all the transitions of E. Okay. And then follows the transitions. And if during the process E ever goes to the enumeration state small e, okay. So if the simulation of E ever enters the enumeration state E, M compares the content of the second step with the content of the third step. Okay, so third step contains the input of the machine M, and the second step contains something that is enumerated by E. Agree? Okay. So if this comparison succeeds, that is, if Y is equal to X, then M knows that the enumeration machine has enumerated X. Okay. So if Y is equal to X, then M accepts by going to its own accept state T. If not, it erases Y from the second step because it's a normal machine tape. So there is no special mechanism needed for erasing things by blanks. Okay. The Turing machine does it, and it continues this simulation of E. Now, if E eventually enumerates X, this will be detected by M. It may take a long time, but it will be eventually detected. Okay. So if A enumerates X at some point of time, M will accept. Okay. And if E never enumerates X, then our M will keep on doing, simulating the enumeration machine forever, perhaps. Okay. Therefore, it follows that E and M have exactly the same language. Okay. Okay. So this is one way of the simulation. The other way is you are given a Turing machine whose task is to accept or reject. I want to build an enumeration machine that will enumerate all and precisely those strings that M accepts. It has infinite time. It can keep on doing this job forever. But if M accepts some string, you will be able to detect that and enumerate by going to that special enumeration state. Okay. So how? So the work tape of E consists of two tracks. Okay. On the top track, the working of M on input strings will be simulated. Okay. And on the second track, bottom track, the input strings themselves are stored. Okay. So the work tape is essentially used by E to simulate the working of M on multiple inputs. In fact, on all inputs, one by one, not one by one. Actually, I will come to that little later. Okay. So this E simulates M on all inputs over this. Okay. And if the simulation lets the machine M to go to the accept state, okay, it will copy the input from the bottom track to the write only output tape and go to that enumeration state. Okay. So it copies the input whenever some simulation detects that the machine has accepted it, it will write that input from the bottom track to the work tape and go to the enumeration state. Okay. Enters the enumeration state. There is a small thing here this enumeration machine has to handle, and in fact we will see in future that Turing machines will also handle this kind of situation. Okay. So this is what is called time sharing, and it is very, very important. Okay. Now this enumeration machine is doing this thing, but in future our Turing machines will do this kind of time sharing. Okay. So what is the problem? One possibility is it will write an output on the bottom track. Okay. Simulate on the top track. Okay. And if the machine accepts, this will enumerate as I have mentioned. But I am not given the fact that M is a total Turing machine. It is not bound to halt on all possible inputs. On some inputs, it may loop. And if that thing happens, the simulation of simulation of M by E on that particular input will never end. Okay. So how will E go to find out whether the next string is going to be accepted or not? There is a problem, right? You understand? So if some simulation, so this is what is, E must simulate M on all inputs, and if it gets stuck, I mean forever, on one particular input, it will never get the opportunity to simulate on the next input. Okay. So this is not what is desirable. So what you will do, yeah, if such a thing happens, he never gets a chance to simulate M on other inputs, the remaining inputs. There are always an infinite number of them. And so the idea is that the simulations must not proceed sequentially. First on maybe input epsilon, then on input A or maybe 0, then on input 1, then on input 0, 1, 0, 0. Okay. This way it should not be done. So all the simulation must run in a sense in parallel. Happy? Okay. So how can it run so many simulations in parallel? In fact, there are infinitely many simulations to run in parallel. Okay. So that's the idea. All the simulations must run simultaneously, in some sense in parallel. Okay. So this is what is, I would say, solved by using time sharing. Okay. So what it does, okay, anyway, sigma star is countable. Okay. So I can enumerate all the input strings in some fashion, x1, x2, x3, x4, x5. Okay. In such a fashion that it is possible for this machine E to generate xn plus 1 from xn. Okay. Not a very difficult thing, right? For example, if my input sigma is 0, 1, binary alphabet, and there is this clear thing called the next string. Okay. Treat it as an integer, add 1 to it, and a Turing machine kind of machine is perfectly capable of doing such things. Okay. So we assume that E can generate xn plus 1 from xn, and it will store not just one, but multiple inputs on the bottom track. Okay. And on the top track, it will store the configurations C1, the current configuration on the simulation of M on X1, the current configuration of the simulation of M on X2, and so on. So what is the configuration? It consists of 3 things: content of the tape, the current state, and the position of the head. Definitely the tape is always infinite, But at all finite amount of time, only a finite part of that tape will be used. The rest of this will be blanks. And there is no need to store those infinitely many blanks. Okay. Therefore, a configuration, although it looks like storing some infinite thing, it is actually a finite. Okay. And so this is fine, right? C1, C2, C3 configurations. These are these things. And when he starts a new simulation, I will tell you how to start a new simulation, xn+1. It will simply append xn+1 hash to both these states. Not exactly, because on the top track, you have to maintain that it is a start state, the head is positioned here. Some little bit extra thing than this xn+1 hash. Okay, some more symbols. Okay. So it does so. And if some configuration expands because the visited part of the tape is increased, okay, then everything that is following that will be relocated. Agree or not? Okay. So if some CI expands, everything to the right of it is shifted to make room for this expansion. And that will be a very large string, but still it is doable. After all, this machine E has eternity. It can run as long as it wants. Okay. And E simulates M in this fashion on X1 for one step, then on X1 for one step, X2 for one step, then on X1 for one step, X2 for one step, X3 for one step, and so on. So that means eventually some session on the nth input xn will start, and periodically it will get its time. Okay, I would not say periodically, not in the sense, proper sense. Eventually it will get time. Every simulation on xn will get enough time to reach completion and go to the accept state whenever some xn is accepted. Okay? So this is what is meant by time sharing. It's not an efficient process, but given such a primitive machine, what else can you expect? Okay. Yeah. So, but this concept you remember. So if you accept some xi, the simulation will eventually detect it. Okay. If it accepts in, let's say, 1 million steps, eventually the simulation of M on xi will have this 1 million steps. Okay. It may happen, I mean, something like after maybe 1 million square steps or something like that, but that is fine. Eventually it will be detected. Happy? Okay. Okay, so I think that is it, and here are some exercises for tutorials. We will solve some of this later, but anyway, we have lost quite some time. Let me switch to another topic and let us see how much we can proceed today. In fact, what happened to the other section is that they do not have any, I mean, they are not making, what is that called, team recording and all that stuff. So they have actually completed whatever I have completed up to this point yesterday itself. Okay. We are running a little slow, and I went there and found that she is still teaching. Okay. We are just waiting for the power to come back, but she is continuing teaching. Anyway, somehow we'll see how we can synchronize our progress. Anyway, so non-deterministic Turing machines is something that we are going to study. And then another formalism, equivalent formalism called unrestricted grammars. But let us see how much we can do about this non-deterministic machines. Okay. So far, we have always seen deterministic machines. Non-deterministic machines we have seen in other finite automata, push-down automata, and all that stuff. But what happens if I allow my Turing machines to be non-deterministic? Do I gain anything? Okay, so that is the question. So by definition, we always consider deterministic Turing machine. So whenever I say Turing machine, I always mean a deterministic Turing machine. And if I want to highlight that that machine is a deterministic, I sometimes may use DTM. Okay. And likewise, I introduce non-deterministic Turing machines and use the abbreviation NTM. Okay. As usual, each NTM has a transition function of this form. In state P, reads A. There are multiple possibilities. We go to state Q1, replace A by B1, move to direction D1, and so on. There are K possibilities for some K greater than equal to 0. If K is 0, the machine is stuck, exactly as it happens for PDA or NFA. Okay. And if K is greater than equal to 2, then the machine chooses one of these K configurations or a K transitions non-deterministically. Okay. It's exactly what happens for non-deterministic machines. And I will use this maximum possible value of K in a transition in the last slide to do some kind of work. We'll come to that. That is called the maximum fan out or fan out, and I will use the symbol F for it. Okay. How many ways the computation can proceed starting from a given point? Okay. Immediately. So that is called the fan out, F. And the machine accepts if and only if some sequence of guesses lead to the accept state. Exactly as in finite automata, non-deterministic finite automata or PDA. If there is a T, then it accepts. And if the guesses are incorrect, then anything may happen. Okay. So other non-deterministic choices may lead to stuck position, even when this is an accepting string. Or other choices may let the machine loop or even end up in reject state. All these things are possible. But if there is a sequence of correct then the machine accepts. Okay. The usual thing. Now, this is one important thing, computation history. The machine starts with an initial configuration. At that point of time, it has multiple choices, possibly. Okay. It does this thing, this thing, this thing, this thing. Okay. And then, for each such choice, there may again be some multiple possibilities. Okay. This. So eventually, I can view the set of computations that the machine can do as a computation tree. Yes or no? Okay. And each path, starting from the root, which is basically the start configuration, to any node in the tree, is called a computation history. I made in the first step, this choice here in the second step, this choice here in the third step, and so on. and a history may terminate in accept or reject state. That's called a terminating history or finite history. Or it may also terminate in this stuck condition in some state, which is neither T nor R. Okay. So these are examples of finite computation history. Starting from the start configuration and reaching somewhere, either an explicit decision, accept or reject, or stuck. You cannot proceed further. Whereas certain deterministic choices, sorry, non-deterministic choices may allow the machine to loop. So these are actually infinite computation histories. Okay. So in terms of computation histories, the non-deterministic machine accepts an input if and only if there is a finite computation history ending in the accept state. Natural, right? Not much to understand. Similarly, if there is okay, something like this, if all computation histories are finite and none ends in the accept state, then this is essentially equivalent to explicit reject. And looping means, okay, explicit reject is clear, right? Okay. And implicit reject, there are no accepting history along with one or more, possibly one or more infinite histories. Okay. Okay. And you see that a specific reject state is not needed, but you can have it anyway, doesn't matter. The language of an NTM is a set of all input strings. It accepts. And NTM is called total if all histories on all inputs are finite. So there is nothing like a looping behavior. Okay. Oh, these are just formalizing the things. And as I mentioned, all histories start with the initial configuration, the start configuration. And depending upon these choices, I have a tree. And that tree may be infinite if there are infinite histories. Okay. So, okay, so here is an example of a non-deterministic Turing machine. And I would like to build a Turing machine for this language, a power n, where n is composite. Something like 4, 6, yeah, 4, 6, 8, 9. Okay. So what this machine does, because a multiple tape machine may be simulated by a single tape machine, so I can design multi-tape machines whenever it makes sense, whenever it simplifies life. Okay, so I will design this as a 2-tape machine. Input a power n is supplied to the first step. Okay. Initially, you just check whether n is 0 or 1, then simply reject. Okay. 0 and 1 are not composite. Then, okay, so instead of looking at this explicit details of what the machine does, I just give you an idea what this machine actually does. On tape 2, it guesses a potential divisor d of n. So it writes a power d. When it stops, that is its non-deterministic choice. Keep on writing a d times, and what that d is, that may be a non-deterministic choice. Okay. So it will actually make a non-deterministic choice between 2 and n minus 1. Okay. So once, or maybe square root of n, whatever, it doesn't matter. The square root of n is difficult to compute, so let's say n minus 1. And then what it does, so it has a power n on its first step, it has a power d on its second step. Okay. All it wants to check is whether this n is a multiple of d. So how do you do that? For you have ds on the second step, erase some ds from the first step. Once again, make another pass, erase some ds. Okay, and keep this. Okay, so if this d actually divides n, then what happens? After some pass, this will be completely erased. Okay, and after the complete, erasing pass. Okay, so this is basically it does. You can just read it out. So what is the non-determinism here? It is basically guessing a potential divisor d of n. Okay. And if that can be guessed, if n is composite, it has a potential divisor. It has a divisor in the range to 2n minus 1. And some non-deterministic guess will eventually, we will find this d. Then it will make the division of n by d. And that division will succeed. It will say yes. But even if n is composite, there may be other choices of d, which are not actually divisors of n. For those things, it makes a division, finds that n is not divisible by d, it will say reject. That doesn't matter. But if n is not composite, or 0, 1, 0 or 1, it is prime, right? Then whatever you guess for d, you can never accept. Because a prime does not have a non-trivial divisor. So all non-deterministic choices will fail. On the other hand, if n is composite and not equal to 0 or 1, then definitely one guess will succeed. Agree or not? So this is basically the working of this Turing machine, and this is how we can exploit non-determinism in the context of Turing machines. Okay. So now I want to show that. Of course, one possibility is that, okay, you can call every deterministic Turing machine a non-deterministic Turing machine, because for every possible combinations of P and A, there is a unique possibility, and I can write that as a singleton set. K is 1. Okay. So the converse thing, given a non-deterministic Turing machine, I want to simulate that Turing machine, the work of that Turing machine by a deterministic Turing machine. Okay. That involves some effort. This can be done. Okay. So first of all, I need to encode configurations, and a configuration consists of 3 things. I keep on repeatedly saying this: state of the finite control, content of the tape, and the head position. These 3 things somehow I have to encode in the form of a string. There are many possibilities. It can be something like this: state is P. Okay. Then I have some string followed by A. And if I use a marker like underscore, then I know this is the head position. This is followed by some V in gamma star. Okay. This is a possible way. Whatever it is, I can also use this encoding. Okay, U instead of underscore, I am just writing P here to denote that this is the state. And This is the symbol A, before which this P, that means A is the current position of the head, V. And of course, in order that this P does not interfere with the symbols in U, A, and V, I assume that Q intersection sigma is empty. Okay. Okay, so there are multiple ways of doing these things. And if I do this, this is the initial configuration. The input is W. This is followed, this will come after this left end marker. That is the content of the tape. Whatever is below, that is filled with blanks only. I do not need to store. This is an unvisited part. And the state is S, the start state. And the head is looking at this initial end marker. So S is here. So this is the initial configuration. Okay. And an accepting configuration will be UTAV for some UA and V. Okay, if the state is T, then it's an accepting configuration. Okay, whatever U or V or A is, it doesn't really matter. Okay. Okay, so as I mentioned, for every NTM N, there exists a DTM D having exactly the same language, and also conversely, but that is obvious because a DTM can be considered as an NTM. The same machine will work. So this thing I have to establish. Okay, so this is what I meant by the computation tree. Okay, C0 is the start configuration. At that point, let's say there are three possibilities. The configuration may change to C1, it may change to C2 or C3. On C1, let's say there is only one possibility and the configuration can change to only C4 and so on. So this is a part of the computation tree. Okay. This somehow has to be explored by the DTM, and this is basically the idea. What the DTM does, it makes a breadth first traversal of this tree. But the tree may be infinite, and therefore this breadth first traversal may never halt. That is fine. Okay. But there is an accepting configuration that will definitely occur somewhere at a finite depth in the tree. Okay. And if I make this BFS, I will eventually, the DTM will eventually go to that level and detect that this is a accept configuration, and it will say yes. It will go to its own accept state and accept. Okay. So once again, I designed this DTM as a two-step machine. So this first step will store the configurations as a queue. The breadth first search requires a queue, right? So this will maintain a set of configurations. So here it will be C0, C1, C2, C3, C4, C5, C6, C7, C8, C9, C10, C11, and so on, right? So this configuration, queue of configurations will be stored here. And because you have infinite space following this, there is no need to, clear this space. Okay. So at any point of time, some configuration is active, which is basically in the front of the queue. The previous things are already explored. So you go to the front of the queue. So this is C5 as shown highlighted here. So this is the current configuration. And this may, for example, be denoted by the special marker, this hat. It says that C5 is the current active configuration. Then what will you do? It will look at the transition function of that non-deterministic machine and you will find out what are the possibilities. Okay. So from that configuration, it knows where the head is, what it is scanning, what the current state is. Okay. and it consults the transition function of n to determine what are the possibilities. Okay, so if there are k possibilities, it will make a copy of this current configuration k times here. Okay, and depending on what the transition possibilities are, it will convert this configuration C5 to C9. Then it will convert the configuration C5 to C10 in the second copy. Finally, there is a third possibility, so it will convert C5 to C11 here. Okay. So that means exploration of all the things that can be reached from C5 in one step. Okay. Then what it will do? One by one, it will copy this C9 here, C5 or C10 here, C11 here. So that will basically NQ. And then it will simply move this hat from this to this next one. Okay, so that's how this TTM simulates the work of the NTM by making a depth first search by making a breadth first search. Okay, in a possibly infinite computation tree. Okay, so maybe I just take 5 more minutes. So this is clearly written here. So I have already explained this. So first step is queue of configurations. Second step is just used as a scratch step to compute the next configurations and separated by hash. This is the initial. And they'll just read this. I've already explained this. Okay. So BFS traversal, yeah. These computations are important. So D makes a breadth first traversal in the computation tree of N. Okay. If N is total, that means it does not have any infinite computation histories. That means the tree is finite. So if N is a total Turing machine, the simulating machine is also a total Turing machine because it has only a finite tree to explore. It will eventually stop. Okay, when all the nodes in that tree are explored. Okay, and if n is the number of steps in the longest computation history of n on some input, okay, so I am restricting to total Turing machines. Okay, if n is the maximum number of steps, then what is the running time of this breadth first search? Now recall that we have defined fan out. What is the maximum number of possibilities that one configuration change in one step? It is true that it's not necessary that all the steps will have the same number of possibilities, but this will definitely give me a worst case behavior. Okay. And if n is the maximum length of computations, running time, so that means how many steps are there. So what is the worst kind of or the biggest kind of tree that we can have? A root, f children, each of this children will have f children each. So f square in the second level, okay, f cube in the third level, and up to the nth level, it will be f power n. Okay. So how many nodes? So 1 plus f square up to f power n, which is basically, I assume that f is a constant, which is essentially big O of f power n. Okay. And running time will be big O of f power n times L, because the change of configuration actually requires locating that, what is that called, that state in that configuration and doing some local changes, right? So it's something like L f power n. So what you look at this is that the original NTM, if it accepts in n steps by making some non-deterministic choices. So I don't know. Nobody knows who will tell you this is the correct choice here, this is the correct choice here. So there is something like dark matter, okay, or dark energy that guides it to make the correct choice. The NTM takes only n steps. Whereas this DTM, you see that n, it's a function of n, but n is appearing in the exponent. So there is an exponential slowdown. From n step to something power n. Okay. And the question is this exponential slowdown unavoidable under certain situations? Or I can simulate the working of the NTM in a more clever manner such that I can avoid this exponential blow up in the running time. Okay. This is basically an unanswered question. And this essentially leads to the so-called P equal to NP problem. Okay. So, what can I do? Actually, we have another thing, unrestricted grammars. Anyway, we will take it up in the next week, or if needed on Thursday. Let us see how we can synchronize, because the next thing is supposed to be covered in the other class. Okay. Because of this power cut, otherwise we could have started this and I will be slightly lagging behind the other class. I don't know. Now I have a complete module left. Anyway, let us stop today here. We will see how we can proceed. Okay, see you. And afternoon we again have a class, but that will be in online mode. Okay. Although I think we have a classroom for that, but anyway, for that, let us continue this online mode. Huh? Programming. What class? Tutorial class, I think we will try to do something here. I have not yet worked out how I can work out something. If I do it on the Blackboard, this Teams people will not be able to see. Okay. So there is a possibility of using this camera. So I will write something here. We will try. Okay. And if we see that this is not possible, then we will, conduct the tutorials in the online mode. This class is I think this is fine. Okay. But today's lab, that will be in online mode as it has been happening. Okay. Okay, so.
Thank you, sir.
Okay. Okay, so team members, do you have any query? Okay, if not, let us stop.